Sorry for the interruption. So the 3-bit representation is magnitude and 1-bit representation is the sign. So this representation is known as sign magnitude representation. So here you can see a circle where the numbers are represented in its sign magnitude representation. So here the numbers can be represented. The numbers can be represented from +0 to sorry, -0 to -7, +0 to -7. So here the range of these n-bit numbers is that the plus or minus 2 raised to n minus 1 numbers can be represented. If we say there are four bits can use to represent a number. So 2 raised to 4 is 16, minus 1 is 15. So it is plus or minus 15. So plus or minus 15 representation can be done in this way. That is +0, +1, 2, 3, 4, 5, 6, and 7. All these are positive numbers. Whereas when the MSB is turned in 1, then the number is represented as negative number. So it can be represented as 0, -1, -2, -3, -4, -5, -6, and -7. So the we can represent the number from -7 to +7, where it is the 15-bit representation. So this is the sign magnitude representation. So sign magnitude representation can be used for addition and subtraction of a number. So here we can have the examples of addition and subtraction of numbers. So we have taken a very small example where we'll be adding 3 plus 4. So here by default 4 is a positive number, as we have not specified any sign, so it is considered as positive. So the equivalent positive number for plus 4 is 0, 1, 0, 0, and the sign is not specified in front of 3, and this plus is the operation which we need to perform on these two operands. Okay, so the addition is +7. So if we perform the same uh, addition or same addition with the negative numbers, so minus 3 plus -4, or -4 plus -3 will give us -7. That's quite obvious. So it has been implemented over here. So you may observe here the sign magnitude, the sign of each number is 1, so it is represented as negative, and the number over here is also represented as 1. So this is quite evident that we can perform both addition and subtraction of the sign magnitude sign numbers. So in order to perform the subtraction, if we have a different what do you call sign of the operation, the result depends on the sign of the number of large magnitude. So here the large magnitude of the number is minus. So the -4 plus 3 is 1, whereas here -4, sorry, +4 minus 3 is 1. So here the number is very much clear that this is positive 1 and this is the negative 1. So here the rules is been given. If r is equal to x minus y, if x is greater than y, subtract y from x, sign of r will be sign of x. If x is smaller than y, then subtract x from y, sign of r will be sign of y. So this is the rule for binary subtraction. So is it clear? If you have any doubts, it's pretty simple, and we have performed this such no operations since your school days. So we'll move on to one's complement representation. So one complement's representation can be done by negating the number. Okay. Say for example, if I say, I'll take a small example for this. So how we can, do you know how we can perform the one's complement of a number by converting this or by negating this number? Negating means the converting 1 to 0. So 1 can be written as 0, 0 can be written as 1, 0 and 0. So this is the one's complement of this number. One's complement of this number. So here we are representing, or we are looking at the aspect with respect to the sign magnitude. So there are some disadvantages of sign magnitude, because there is cumbersome addition or subtraction. Must compare magnitudes to determine the sign of the result. So to overcome this problem, we are dealing with one's complement representation. So one's complement representation can be done when n is positive, then n bar is negative of one's complement. So n bar is equal to 2 raised to n. N is number of bits, minus 1, minus 1. So the example is one's complement of 7 is 2 raised to 4 is 16, which can be represented like this. So minus 1 is nothing but this. So we are subtracting 1 from it. So it is nothing but 15. So we can have 15 representations of one's complement, that is in one's complement. The shortcut is from this. Okay. So bitwise complementing and performing the required operation. So we'll move on to the next step, that is one's complement representation. So here the numbers or the representation is changed, whereas in the previous slide the represent 1000 was minus 0, whereas in one's complement representation that is 1111. So here we will see how we are no representing the positive and negative numbers with respect to one's complement. So the most significant bit represents the sign of a number. So the MSBs, wherever there are zeros, are the positive number. So from plus 0 to plus 7 is represented here. So 0000 is plus 0, 0001 is 1, 0010 is plus 2, this is plus 3, plus 4, plus 5, plus 6 and plus 7. So if we perform the ones complement on this, so it is equivalent to minus 7. This is minus 6, minus 5, minus 4, minus 3, minus 2, minus 1 and minus 0. So I ask you a question out of curiosity. So can you tell me, can we have plus 0 and minus 0? Is it possible? Can any one of you answer?
No.
No, right?
No.
So this
Zero is neutral.
0 is neutral, right? It doesn't have any sign. So in this representation, it has been observed that 0 has the sign. So in order to eliminate that, we again move on to 2's complement representation. So 2's complement representation is nothing but, so here in this diagram you may observe that the minus 0 has been eliminated and the 0 is neutralized if you eliminate this plus sign, so it represents 0, so it doesn't make any sense if we write plus or no, not. Okay, so in two's complement representation we are eliminating the problem of one's complement, so we can have n number of two's complement numbers, so that can be 2 raised to n minus n. So here the how we will see, we will take an example and we will verify whether it is working fine or not. So we will consider plus 2 and we will convert that plus 2 in minus 2 using 2's complement number. So we will verify it. Plus 2 is 0 0 1 0. I'll perform 1's complement on this 1 1 0 1, and I will add 1 to this, so which will, this is 1's complement. If I add 1 to 1's complement, then it will become 2's complement. So 1 plus 1 is 0, carry 1, so 1, now 1 1. So we can see that the minus 2 is equivalent to 1 1 1 0, so which we have achieved here. We'll take another example of plus 5 in order to verify it thoroughly. 0 1 0 1 is the number for plus 5, so I will convert it into 1's complement, so it would become 1 0 1 0. If I add 1 to it, it will become 1 1 0 1, so which is minus 5 over here. So here it is quite easier for the representation of positive or I would say signed numbers by using 2's complement representation. So here we are again dealing with many problems of or the examples for 2's complement addition and subtraction in the following sections. So this is how we are performing 2's complement of a session. So this is the representation they have considered as an example. What they have done is 2 raised to 4 is 16, though they have subtracted 7 from 16, so it is 1001, so which represents minus 7 over here. Okay, so this is the another way to convert the a number to its 2's complement equivalent number. So I hope the message, this particular example is quite easier for us to, in order to perform the, or in order to convert a number in its 2's complement form. So this is how 2's complement form is done. So here we'll verify few examples for this. So let me erase this and we'll see the examples one by one. Please the underline, we have it has been underlined that assuming no overflow. Okay, adding carry out sign to LSB. Okay, so here we are performing one's complement calculations. So how we perform this? Add two n-bit numbers starting from LSB. So we are adding these two numbers, that is minus 4 plus minus 3 starting from LSB. If there is an end carry into position n plus 1, then remove the carry and add it a 1 to its LSB. Okay, so there is a carry, so we will see that one by one. So here there is no carry at the end, so it is not and the round of carry. So here 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, and this is the carry 1 which it has been asked to add to the LSB. So if we add 1 to this, so it will be converted into 1000. So if we do this, so if I write plus 7, so it is 1 1 1, and if I consider the ones complement representation of 7, which will convert it into 0, so it will become 0 0 0. So this is -7 representation which we have achieved. So there is another example over here where we are performing the subtraction of plus 4 minus 3. So the plus 4 minus 3 is nothing but a 1. So there has been there is a end carry out, so which is added to the LSB of the result. So the equivalent number is plus 1. So in this example, in this example, 1 plus 1 is 0, 1 plus 1 is 1 and carry 1. So this is 1, and 1 plus 0 is 1. So there is no carry out. So this representation is nothing but what called minus 1. So is it clear? Examples are clear to you? Are they
Yes, sir.
fine? So we will move on to the next example. So here the case has been given which we have discussed in the previous example. So it's same. So we'll not waste our time in discussing the same example repeatedly. They have given the steps which we have discussed right now. So now we will move on to the next number system, or next addition and subtraction of 2's complement number. So we will see here that if there is no overflow method, sorry, so if there is no overflow method, add two n-bit numbers, add two n-bit numbers starting from LSB, discard the carry out of the sign bit. So if there is any uh, carry from the MSD or from the sign bit, just we need to discard. So if there is any carry generated at MSB, then that condition is known as overflow condition for 2's complement. If carry out into sign bit differs from carry out of sign bit, then the result is an overflow. Okay, I'll repeat it. If carry into sign bit differs from carry out of sign bit, then there is an carry out. For say for example, if we'll see this example, so this statement will become clear. So 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 0 is 0. So is there any carry out of this sign bits? There is no carry out, so there is no overflow. So we'll consider this. 1 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 1, carry 1, 1 plus 1 is 1 and carry 1. So this one is not different from the MSB. So there is no overflow over here. If this was 0, then that would have been, or if the sign bit has was 0 and the carry out is 1, then it would have been considered as an overflow condition. Is it clear? Overflow condition clear here? Okay, so this overflow condition, so in this case here, if we consider 4 minus 3, that is 1 plus 1 is 1, 0 plus 0 is 0, 1 minus 1 is 1 plus 1 is 1, carry 1, 1 plus 1 is 0, carry 1. Here the sign is 0 and the carry out is 1. So in this condition, we will be considering it as an overflow condition. Okay, and we are discarding this carry out from the result. Okay, so this is how they have explained, what we have discussed now. So that's all for today's session. I hope once we have discussed today the sign numbers, that is sign magnitude, one's complement representation, and the operation performed on that are addition and subtraction. We have discussed about two's complement. So there was a problem in the sign magnitude representation because of the addition and subtraction was very cumbersome in sign magnitude representation. So uh, one's complement was recommended, but the one's complement has the problem of plus 0 and minus 0. So in order to eliminate that, two's complement was recommended. So we have saw all the pros and cons of each representation and how the addition and subtraction are considered for all the examples. So is it clear?
Yes, sir.
Any doubts in the session?
No, sir.
If no, then drop down your attendance in the chat box. Yes, Rohit, any doubts? Students who have given the attendance may leave the session.
Sir, can you provide the notes for the particular subject?
Sorry, you are not audible.
Can you provide? Hello, sir.
Yeah.
Hello.
Yeah.
Sir, can you provide notes for this particular subject?
Yeah, I will provide. I will be providing. Notes are already available on the Moodle. You may access it, but I need to organize them. Yeah.
So, sir, there are internet issues. So many times your voice is breaking or not audible. So I would prefer to learn the subject from the notes.
Yeah, sure. I'll share the notes. It's already on the Moodle. You may download it from Moodle. If it is not accessible to you, you just ping me on. Yeah.
Sir, I checked on Moodle, but it's not that elaborated as you teach over here.
Okay. So
I
I'll
went through the notes last time.
Fine, I'll provide you the notes.
Okay, thank you, sir. Thank you, sir.
Yeah. Students who have given attendance may leave the session.